Now, we very rarely find free fatty acids in cells. The free fatty acids, because of their carboxylic acid group, are toxic to cells, in fact. So most of the fatty acids are converted to some storage form or to a structural lipid. The storage form of fatty acids is triglycerides. The structural lipids are things like phospholipids and sphingolipids, as we've indicated below. Triglycerides and phospholipids both involve the addition of fatty acids to glycerol 3-phosphate. And so there's a formation of a structural or storage lipid on a glycerol backbone. Now, glycerol 3-phosphate comes from a couple of different sources. It may be recycled glycerol from the degradation of glycerolipids, or it can be synthesized from glycolytic intermediates such as dihydroxyacetone phosphate, as we show below here. So dihydroxyacetone phosphate can be converted to glycerol 3-phosphate, as can free glycerol. So using that glycerol 3-phosphate, then we can make triglycerides. And triglycerides consist of a molecule of glycerol with a fatty acid bonded to each carbon via an ester linkage, as shown here. Because they're predominantly hydrophobic, triglycerides tend to aggregate with each other in oil droplets, mostly in fat cells, which are also called adipocytes. Triglycerides are broken down by specific enzymes that are called lipases, and these lipases cleave the free fatty acids from the glycerol backbone. Now, there are two of these that we'll consider. One is lipoprotein lipase, and that cleaves triglyceride in the blood for transport into cells. And we'll talk about that later when we discuss lipid transport. There's also a lipase called hormone-sensitive lipase, and this cleaves triglyceride in cells, mostly in adipocytes, for transport to other cells for oxidation. It's called hormone-sensitive because it responds to glucagon in releasing free fatty acids in the fasted state to produce more energy. Phospholipids are structurally similar to triglycerides in that they have the same glycerol backbone. But instead of a fatty acid at one of the carbons of glycerol, there's a phosphate attached to a polar head group, as shown here. So here at the third carbon of glycerol, you have a phosphate group, and this is attached to a molecule of choline. That's what this particular molecule is, to form phosphatidylcholine. Now, we can add a variety of head groups to this phosphate. And this creates what we call the 5 major phospholipids. Ethanolamine, which creates phosphatidylethanolamine. Choline, as we showed in the previous slide, forming phosphatidylcholine. Serine, which forms phosphatidylserine. Inositol to form phosphatidylinositol. And glycerol to form phosphatidylglycerol. The major function of these phospholipids is to create cellular membranes. Now, the phospholipids are what we call amphipathic, meaning that they have both hydrophobic and hydrophilic structures. The hydrophobic structures are the acyl chains that extend from the fatty acids attached to the first and second position of the glycerol backbone. And then there's a hydrophilic group, which is that head group. So this makes them ideal for forming bilayers, where the head groups face outward and interact with water either in the intracellular or extracellular space, and the acyl chains form inward, interacting with each other via these hydrophobic interactions of the acyl chains, as shown in this schematic diagram below. Now, one of the other functions of phospholipids is in cellular signaling. There's an enzyme called phospholipase C, and phospholipase C takes a molecule of phosphatidylinositol and converts it into inositol triphosphate with diacylglycerol. And both of these molecules act as second messengers, much as cyclic AMP does, as we talked about before in regulation of metabolism. Other enzymes can help to degrade phospholipids so that they can be absorbed from our diet. Some of these are phospholipase A1, which cleaves the fatty acid from the 1 position, phospholipase A2, which cleaves the fatty acid from the 2 position, phospholipase C, which cleaves off both the head group and the phosphate, and phospholipase D, which cleaves off just the head group, leaving the phosphate behind. Now, another type of structural lipid is called sphingolipids. Now, sphingolipids are lipids that are also found in cellular membranes, but they have particular properties and are particularly enriched in nervous tissue. Sphingolipids are composed of a molecule of ceramide, which is sort of similar to the diacylglycerol backbone of phospholipids, and also a head group. And again, there's a variety of head groups that can be added to ceramide to form different sphingolipids. If you add a molecule of choline, we call that sphingomyelin. If you had complex oligosaccharides, you get things like cerebrosides and gangliosides and globosides. These are different types of sphingolipids. If you add a sulfate to it, you get sulfatides. And so all of these different complex sphingolipids then have particular roles in the membranes of cells, particularly in the membranes of nervous tissue. Sphingolipids are synthesized by adding head groups sequentially by glycosidic bonds. So what you end up with are long chains of sugars where it's attached to the head group of the basic ceramide molecule. They're degraded then by removing each of those head groups sequentially using, again, specific enzymes. We describe that process because that process has defects in it which can cause serious disease, as illustrated in this clinical vignette. The parents of a 9-month-old girl bring her into the pediatrician concerned that she's not starting to crawl yet. They say that she doesn't seem to be coordinated enough. She also seems less alert and very sensitive to noise. When you look at the patient's chart, you notice that she started meeting all her developmental milestones, but about 6 months of age, she started falling behind. And at this visit, she seems to actually have regressed. Family history reveals that the parents are both of Eastern European Jewish ancestry. Physical exam is significant for generalized hypotonia. You're concerned about this, so you do a thorough fundoscopic exam and notice that the macula has a bright red spot on it that looks like this. So what disease does this patient have? This patient has Tay-Sachs disease. Tay-Sachs disease is an autosomal recessive disorder that's caused by mutations in the alpha subunit of hexosaminidase. This is an enzyme responsible for degrading GM2 gangliosides. You don't have to know what GM2 gangliosides are, but just recognize that Tay-Sachs disease is a disease that's caused by a defect in the breakdown of certain sphingolipids. The consequence of this defect is that undegraded gangliosides accumulate in the lysosomes of cells, particularly in neurons. And this is because, again, remember that these sphingolipids are particularly enriched in neurons. And this eventually leads to cell death. There's a characteristic feature that you see on electron microscopy, which is these whorled inclusions in the lysosomes, which are aggregations of undigested gangliosides. The initial symptoms of Tay-Sachs disease appear at about 3 to 10 months and include decreased alertness, excessive sensitivity to noise, which is called hyperacusis, that we described before, and developmental delay. The classic physical exam finding early in the disease is that cherry red spot on the macula by fundoscopic exam. The course of the disease is progressive. They have seizures, paralysis, blindness, and dementia. They usually die by the age of 4. Now, Tay-Sachs disease is a prototypic example of the category of disease that we call lysosomal storage disease. It includes other diseases of defective sphingolipid degradation, as I'll show you in just a minute. These diseases are relatively rare, except for in the Eastern European Ashkenazi Jewish population, which shows a higher incidence of both Gaucher's disease, Tay-Sachs disease, and Niemann-Pick disease. So here are some of the lysosomal storage diseases. And these diseases are all defects in specific enzymes which break down the sugars which are attached to sphingolipids. And so in each of these cases, we're unable to break down a certain type of sphingolipid, and so those sphingolipids accumulate in lysosomes and they lead to cell death, particularly, again, in neurons, though it occurs in other places as well. So here's a list of these lysosomal storage diseases, and it would behoove you to know a little bit about each of these diseases. Tay-Sachs disease we already described. There's also a disease called Fabry's disease, which is X-linked, and it's a defect in alpha-galactosidase. It exhibits kidney failure, heart failure, and a reddish-purple rash. Gaucher's disease is a defect in beta-glucosidase. These patients usually have hepatosplenomegaly and pancytopenia, and this is because they get involvement of the bone marrow as well. This leads to pathologic fractures in addition to the pancytopenia. Metachromatic leukodystrophy is a defect in aerosulfatase A and leads to demyelination of neurons in the central nervous system and cognitive decline. Niemann-Pick disease is a defect in sphingomyelinase, and so the thing that accumulates in this disease is sphingomyelin, and they get neurodegeneration, but they also have hepatosplenomegaly. Krabbe's disease is a defect in beta-galactosidase, which leads to mental and motor degeneration and blindness and deafness. This concludes the section on glycerolipids